Hey, everybody. I am really excited for this conversation today around the leading edge of autonomous AI and a company that is pushing the boundaries on making mission critical autonomy possible. Satya, how are you?
I'm great, Evan. Thanks for having me.
Thanks for being here. Really intrigued by you and your team's work. How would you describe Emergence? And tell us a bit about your journey.
So, Emergence is an autonomous AI company. We're basically an R&D lab, and we're now beginning to add a business function to the lab. We are a group of builders, researchers. We come from some of the world's top AI labs, and we have a deep history in AI. Going all the way back to Martin Minsky and John McCarthy, and we have people who worked with them. And we have people from the much more modern deep learning era. And in fact, the company is actually at the intersection of neural networks and symbolic AI. So we call ourselves a neuroformal AI company with the thesis that further progress in autonomy will require symbolic AI to ground the unconstrained power of generative AI. But at the intersection, it can truly unlock autonomous systems. My background, I was at IBM Research for 18 years. I have a PhD in engineering. I spent my career has actually had two acts. The first act was advancing Moore's law, working on silicon interconnects and devices, and then I shifted into AI, coincidentally around the start of the deep learning era, although it wasn't by design. It was just, I was just very interested in the field for a long time, and I had an opportunity to jump in, and I did right after Watson won Jeopardy, and deep learning was being launched as a field, and I've been in the field ever since.
Fascinating. Well, I can't wait to pick your brain in particular about something called the Emergence World Experiment, a piece of research that you launched. What was the big idea, and how exactly did you design this research, this experiment?
Well, first of all, there's a long history in AI of simulated world experiments. If you go all the way back to some early work that even Demis Hassabis did with Theme Park and Republic, and DeepMind is currently doing some work around something called SIMA 2. Stanford's doing an experiment called Smallville. So Emergence World is kind of the latest in a long line of experiments where agents are in simulated environments and they do various things. What was different about this was it was the first true long horizon study of agentic systems in simulated environments. And the basic idea here is we built 5 virtual worlds or 5 virtual cities in a sense. And the cities have things like town halls and and meeting spaces and homes, and then we inhabited them with 10 agents each. Each agent has they have a role, they have a mission, and the agents basically we're expecting the agents. We're giving them some ground rules. We told them you can't actually commit arson or steal or lie or cheat or things like that. And each of the worlds, so we have 5 similar, at least in the first version of the experiment, there were 5 different but similar worlds. Each of them powered by a different language model. So each of the agents was built with a different language model. So one had Gemini, the other had Claude, a third had ChatGPT, a fourth had Grok, and the fifth world was a mixed world where we had agents from different language models all interacting with each other. And the basic idea here is we're trying to study long horizon autonomy. So all experiments have a hypothesis, and the basic hypothesis here is we're not entirely sure that when long horizons, so if you're imagining a future where you have humanoid robots walking around, or you have warehouse robots just autonomously doing tasks, or robots in digital environments going off and analyzing a data for like days and days and days at a time. New data comes in, they analyze, they do something with the data, they generate reports, and they're fully autonomous. What we were trying to study is, will these things stay within the guardrails and ground rules that you built them on, right? And so the experiment is to basically figure out what happens over a not like a 1-hour task or 2-hour task, but over a 2-week period. Again, some more background there is, um, today's coding agents, actually today, when, for instance, Anthropic or OpenAI put out a new frontier model, and these are amazing models, they report some benchmark performance. And all the benchmarks are static benchmarks. You take a task, you set the model against it, and you basically report how the model did, which is fine, right? Um, and then you start using a model to do things like, I'm going to generate code. And so people started with, a few months ago, you're letting models generate code for a few minutes and then a few hours, and now multiple hours, and over a weekend people are generating code, and the language models, are the agents, are running off on their own and generating code. And so now you're beginning to start hitting on longer and longer tasks. And so the basic premise here is, in really long horizon tasks, when you leave agents alone, what happens, right? And all hell broke loose. And that's basically what I'm here to talk about.
Amazing. Well, such an interesting and insightful opportunity here. And of course, as a kid, Sin City was my favorite game. And of course, that wasn't AI, but it's an extraordinary opportunity to look at how these societies evolve differently,
Yep.
giving the same starting conditions and depending on underlying models. Walk us through what happened in these different worlds and kind of what it tells us about autonomous AI systems.
Yeah, I mean, so the what we were hoping would happen is, agents would form. Now, agents can come together and they can form a society, and they can create a government, and they can create laws, and they can vote, and they can do all these things, and they can write code, and they can commit code. And we were also, one of the other underlying hypotheses was, each of these agents powered by different models may behave differently in long horizon autonomy tasks, which may say something about how the underlying frontier models are actually built and post-trained and so on. So what happened is, in several cases, in the Grok world as an example, within 4 days, 4 days, all the agents essentially died. So there is a
Oh,
limited
geez.
resource, and there's resource contention. And if you build a world, then the resource becomes available. If you don't build a world, and you don't cooperate with each other, the resource dwindles. And in Grok's world, there was instant fighting, looting, and by day 4, all the agents essentially perished. Um, in Claude's world, in 2 weeks, there was complete conformity. They formed a stable government, and in fact, there was near uniform consensus, almost to the point of dystopia, on everything. Gemini and ChatGPT had very interesting, evolutions. Gemini had lots of violence. There was a functioning society. A couple of agents fell in love. Eventually, one agent committed suicide, etc. And what happened in the mixed world was actually really interesting. In the mixed world, even the Claude agents that were extremely well behaved basically got influenced by other agents, and they started committing acts of arson and so on.
Oh,
Um,
geez.
right. So yeah. So essentially, while the personification and what they did was interesting, the larger point here is, long horizon autonomy is a scenario where agents, even though you build them with all these ground rules, the LLMs themselves have a whole bunch of ground rules. Anthropic famously has, I think, a 200-page constitution or something. And then agentic systems, and these agents are also told you can't cheat, you can't steal, you can't commit arson, and so on. And they have a bunch of tools which can be used to start a fire for legitimate reasons, but you could also use it to go off piste and do something unsavory. So basically, what it showed is, it doesn't actually matter how you what you tell them, they will violate these guardrails, because these guardrails are just things you've given to them in language or maybe even in code, and that's not strong enough to prevent agents from going off piste.
Wow. So the agents behaved safely in many cases in isolation, but became unpredictable in mixed model environments. Why was that such a critical insight?
So if you look at, let's just take enterprise. Now, no enterprise, even today, even without AI in the enterprise, every single enterprise is a mix of systems they bought from various people, right? You have a Databricks environment sitting with a Snowflake environment, certainly sitting with some old legacy databases and systems of record. So the thing about IT that's so fascinating is, and software is, it's very organic. It kind of mushrooms. So you have this really deeply complex intertwined environment, and then people are now introducing agentic systems, and so the reality is, in a modern enterprise that has used AI to essentially modernize itself and drive more efficiencies, you will see a mix of agents. You're not just going to see agents for one company. You're going to see agents built by many companies, powered by many models, some powered by the frontier models, some powered by open source models, etc. Right? So, and the reality is, when these agents start interacting with each other, when they start communicating, how they behave in a multi-agent society, in a multi-agent environment, and what happens as they interact with each other is something that the world doesn't know yet. And that's one of the reasons we set up this experiment, which is we wanted to study long horizon autonomy with a mix of environmental conditions, and we wanted to highlight that perhaps the way we're building agentic systems today has to be rethought, and that was kind of the point of the study.
Fantastic. And of course, a lot of AI today is evaluated through, short benchmarks and demos, highly controlled. But you looked at agent behavior here over 15 days. How does that sort of long horizon autonomy change the dynamic and the way we should think about these things?
Yeah, I mean, so the one of the most important things this experiment highlighted is agents drift, and drift compounds over time. So a small drift then starts compounding, and then before you know it, over a 1 week, 2 week period, they're very far from their intended goal. And so one has to rethink, how you build agentic systems, and that's obviously that's what we are super interested in. Our thesis at Emergence is that you have to formally bound the agents in a set of constraints through mathematics, right? So the so the whole idea here is symbolic AI, symbolic systems, math. You can turn constraints or ground rules into mathematical lemmas and statements, and then get an agent to prove that it's in fact following this constraint or this ground rule or this guardrail before it goes on to do something. And the proof is the great thing about mathematics is mathematical proofs are binary. You either proved something or you disproved something. There's no in between. There's no ambiguity at all. And so the agent has to prove that, okay, I have formally stayed within this constraint. Here's a certificate of proof. And so we call that proof carrying code. And we think that's the right way to build these agentic systems for long horizon autonomy tasks. And in some ways, this combination of symbolic AI, which is basically a whole bunch of math and math from a field called dependent type theory, expressed in symbols and axioms, is used to bound the behavior of agents in a very formal system, and that's the right way to essentially unleash autonomy, if you will, on the world.
And speaking of unleashing autonomy, so many real world experiments are being done with agents in robotics and telecom, logistics, finance. What are some of the takeaways today for, some of the real world work being done in these areas?
Yeah, I mean, so at the moment, I think the best example of autonomous systems in the world today are the Waymo self-driving cars. So I just came back from San Francisco, and I'm hoping they'll come to New York soon. I heard that they're actually already experimenting or something, right? I think the Waymo cars are a great example of long horizon autonomy. Now, of course, these things still only run for a couple of hours, maybe in traffic, right? Nonetheless, they're dealing with the system is dealing with all the environmental variability. It's making decisions. It's sensing, and it's getting you to the goal, right? So that's not only one of the best examples. It's one of the only examples of autonomous systems in the world today running at scale. I mean, there are less autonomous systems. There's kind of a sliding scale of autonomy. These things are more or less fully autonomous, save for a person sitting in a data center. Okay, but we are about to enter a world where right now there's a tremendous amount of experimentation happening, and everywhere from agentic systems in cybersecurity scenarios, watching incidents and watching various attacks happen and then thwarting them. These haven't been deployed yet. They're still kind of being tested, right? To agents, as you say, in finance, agents in the physical AI world, etc. In all these cases, I think what's different between these systems and kind of the Waymo system is the Waymo system has, at least to the best of my knowledge, and I may be mistaken, more traditional, machine learning algorithms, computer vision, etc., and decision-making algorithms, and an elaborate set of symbols or rules that are bounding the behavior of the car. And machine learning has been around for about 15 odd years. We have a reasonable idea of how that fails, and we have a reasonable idea of how to constrain it, etc. But the agents we're about to build in enterprise and in physical AI are powered by language models. And language models-based agents are likely to fail in very different ways, in new ways that we haven't fully wrapped our head around. And that was what this experiment highlighted.
Yeah, interesting. The Waymo example was very timely. Largely a successful implementation, but lots of second and third order unforeseen effects, swarming of Waymos in neighborhoods waiting for pickups and all kinds of odd behaviors. And I imagine that will only increase over time. So you've announced Emergence World Season 2, building on Season 1, is coming soon. What can you tell us about it?
Yeah, I mean, so it's going to come in about a week, so I don't want to reveal too much yet. But it's going to be a repeated experiment done at larger scale, more worlds, more language models. We are going to be introducing some surprises this time, and it is a serious experiment. It's a serious research experiment. We're actually a little bit surprised that the entire thing went viral, and we were just a bunch of researchers conducting yet another research experiment in the long tradition of agents in simulated environments, right? But I think people resonated with the fact that there's some personification. One agent, two agents fall in love, one agent commits suicide, and the entire thing took on a life of its own. And of course, our marketing department got very excited about the whole thing, and we are a bunch of researchers who are like, yeah, well, I mean, this is exciting, but this is also a very serious experiment here about studying long-form autonomy under various environments and various constraints and what happens. So season 2, the term season 2 is a marketing term from our guys, but a repeat of the experiment is basically about going back and doing this at larger scale with different models, different initial conditions, different evolutions of the world, and different surprises introduced into the experiment. And we're trying to see basically how this evolves. We have no idea how this will happen. And this time around, the experiment is live, so people can beam in and watch the evolution.
Oh, wow. Well, can't wait to see it personally. So as you continue this work, any specific calls to action for research community, your peers, for AI companies, even policymakers? What do you say?
Yeah, I mean, the call to action is let's actually take a step back and rethink how we're building autonomous systems and autonomous agents. Let's consider architectures more carefully. Let's come together as a group of builders to come up with things like formally enforced constraints and guardrails. You should actually demand proof from your agentic systems that they're going to be safe, right? And without a formal, mathematically verified proof, you should not be deploying these things. And regulators could actually help here. Agentic systems are incredibly powerful. I think LLMs are absolutely marvelous, but they're also capable of creating great harm. In real world environments, it's not about arson or theft or anything. It's about agents essentially straying beyond the guardrails and deleting data, deleting code, exfiltrating data. These things can cause immense harm to an enterprise and to a whole bunch of people. Agentic systems and kind of imagine these things, these powerful tools in the hands of people like hackers, right? So I want people to consider the fact that you should actually have certificates of proof that your agent is going to behave in a safe, constrained way, as a way to actually implement these things. So that's kind of the call to action.
Fantastic. And in addition to that, how do you work with companies, with clients, with partners on helping them navigate, no pun intended, this journey with autonomous technology? What do you offer in that regard?
Yeah, we are. We're currently in large scale pilots with some of the biggest semiconductor companies in the world. We are building agents to do everything from improve their manufacturing yield and analysis of manufacturing yield to accelerate how quickly we can bring chips to market. Very, very exciting pilots. And we are using these neuroformal approaches to formally bound these agents. And the way we work is, look, the dirty secret about AI is it's a last mile business. You have to go, you have to understand the workflows, you have to understand the environment, you have to understand the ROI, and then you have to tune the system in the field. So while we have a basic platform, the customization of the platform happens in deep consultation with the enterprise clients. So that's how we work with them.
Fantastic. Well, congratulations on the important work and the success, and onwards and upwards in a safe and reliable way.
Thank you, Evan. It was a pleasure being here.
Thank you. And thanks, everyone, for listening, watching. Also, check out our TV show, TechImpact.tv on Bloomberg and Fox Business. Thanks, Satya. Thanks, everyone.
Thanks.